In the last two previous videos, we have investigated linearly polarized microwave. This means that its two orthogonal components of the electric field oscillation are in phase. This can be indicated by zero reading when the receiver is perpendicular to the axis of the microwave's electric field. Another way to say it is that the magnitude of one of the electric field components is zero. That was actually a special case of the more general type of polarization, which is elliptical polarization, where the phase difference between two orthogonal components can have any value. The other special case is circular polarization, where the phase difference is a quarter of the wavelength. Hence, the magnitude of the electric field is held constant, while the direction is changing over time. This also requires that both components have the same magnitude. The direction of the rotation can be clockwise or anti-clockwise, depending on which component is ahead in phase. An elliptically polarized microwave can be obtained by shifting one component of a linearly polarized microwave relative to its other component. This can be done by passing to a birefringent material. Another way is by making one component to travel further than the other. From previous video, we know that a metal grid will reflect microwave component which is parallel to its metal alignment, while transmitting the perpendicular component. Thus, we can reflect the transmitted component behind the filter, so they have to travel further before joining the other component. The result is an elliptically polarized microwave whose phase difference between its components depends on the orientation of the transmitter, incident angle, and the distance between polarizer and reflector. This is the equipment we are going to use to convert a linearly polarized microwave into an elliptically polarized one. It consists of a metal grating that acts as a polarizing filter, and a metal plate as a reflector, which is taped behind the filter. As you can see here, the distance between the front face of the filter and the front face of the reflector is 8 mm. First, we arrange the setup at a small angle of incidence, as convenient to keep the free space to rotate the axis of transmitter as well as receiver. The distance is kept short in order to get adequate intensity as we rotate the transmitter and the receiver. We can see the received intensity drops as we rotate the transmitter to about 45 degrees. When the receiver is also rotated, the intensity drops further, but unlike the experiment in the previous videos, it never goes down to zero. It goes back to maximum value as we rotate the receiver further. This clearly shows that the microwave at the receiver is elliptically polarized. The setup now is almost identical to the setup just before. The only difference is the incident angle of reflection, which is significantly larger. Just like before, the receive intensity drops as we rotate the transmitter to about 45 degrees. But when the receiver is also rotated, it drops down to zero at some axis angle. As we rotate the receiver further, it is found that the microwave again almost linearly polarized. From the last setup, the receiver is rotated to make the intensity reading nearly zero. Maybe some of you will think that this is just the same as what an ordinary metal reflector would do when the axis of the receiver is perpendicular to the transmitter. Let's see what a metal reflector would actually do by flipping the reflector to the front side. The receiver gets high value instead. The receiver gets zero reading when it is rotated 45 degrees in the opposite direction. From this observation, it is clear that previous setup has actually rotated the orientation of the microwave axis by nearly 90 degrees.